All right, welcome to sections 5.3 and 5.4. So for 5.3, we're going to talk about exponential and logarithmic equations now. So we talked about exponential versus logarithmic and how to convert back and forth and all those logarithm rules. Those logarithm rules are very, very important. You need to make sure you know those for all math classes you take from this point on. All right. So now we're going to solve some exponential equations using logarithmic forms. So to solve an exponential equation using logarithmic form, first rewrite the equation with the term containing the exponent by itself on one side. Divide both sides by the coefficient. So remember, a coefficient is a number in front that's being multiplied by the exponential function of the term containing the exponent. Change the new equation to logarithmic form, and then solve. Okay, so that's what we're going to do here. All right, so if we want to get t by itself, that's our goal here, but t is in the exponent, so that gives us a little bit of an issue. But like they said, first thing, let's get this thing with the exponent by itself first. Okay, to do that, we're going to divide both sides by 150. All right, so if you do that, 3,000 divided by 150 is 20, and that's going to be equal to 10 to the 4t power. Now what we're going to do is we're going to convert to exponential form. Okay, so remember how we convert, right? So we're going to use kind of the opposite of the loop around thing. So we're going to say log, it's going to be base 10. So when there's a base 10, so I'll put the 10 in there, but remember you don't have to write a base 10, of 20 equals 4t. Now we can check it and make sure we did it in the right order. Remember the loop around I showed you? So we should say 10 to the 4t power equals 20, and that's what we have here. So we did it right. Okay. All right, we want t by itself, so we'll simply divide by 4. And there we go. T equals log of 20. Again, we don't have to write a base 10, that's implied. Divided by 4. Now you're welcome to plug this into a calculator, but if you do, be sure you put parentheses around that 20, then hit divided by 4. Okay? And also do not be tempted to divide 20 by 4. Okay, it's not log times 20, it's logarithm of 20. This is one piece. We cannot break the log and the 20 into pieces here. Okay? Very important that you know that. All right, change of base formula. This is also for logarithms again. Basically what this was originally for was way back in the day when calculators could not handle any base other than 10 in their calculations. Now most of them can, or the newer ones can at least. But we still need to know this formula. You're going to be asked some questions on it. All right, so let's see. If b is greater than 0, in other words, if b is positive, not equal to 1, if a is positive and not equal to 1, and x is positive, then log base a of x is the same as saying log base b of x over log base b of a. In other words, what we're allowed to do is pick any base that we want, any base that we're allowed to use, and we put the bigger one, log of the bigger number, over log of the smaller number. Okay, in other words, logarithm of the argument divided by logarithm of the base. Okay, so there's a couple different forms here. We could use log of x over log of a. We could also use natural log of x divided by natural log of a. Okay, these are all equivalent. You'll get the same answer. Okay. All right, so let's evaluate this one. It says evaluate with a calculator. You can do that by plugging in, but we can use the change of base formula, right? So again, most of your calculators now will do a log base 8, but for those of us that have an older calculator, let's just do it with the change of base formula, okay? In other words, we do log of the bigger number, 124, bigger as in physically larger, not numerically larger, over log of the base. And again, when you type these in, please make sure that you use parentheses. Okay, just like I did here. If you plug that in properly, you should get 2.318, somewhere around there. Okay, make sure you try that out. Make sure you know how to do those. Okay, so here's another example. Investments. So if $10,000 is invested for T years at 10% compounded annually, the future value is given by this equation here. So they're being nice, they're giving you the equation. But they want to know how many years will the investment, in how many years will the investment grow to 45,950? Okay, so in other words, they want us to find T. Okay, so let's do that. Well, they're saying the future value, this S value, is 45,950. So we're going to plug that number in for S and then solve for T. 45,950 equals 10,000. And again, make sure you use your parentheses properly, just like I did here. Oops, 1.1 T. Okay, so we'll divide by the 10,000. All right, and we'll get 4.595 equals 1.1 T. Again, we're going to convert to logarithmic, just like we did before. So we'll do log base 1.1 of 4.95, oops, 4.595 equals T. Okay, and again, if you have a calculator that can handle it, you can plug that in exactly like that. If not, we can use the change of base formula. So we can say T equals log of the argument, 4.595, divided by log of 1.1. And again, make sure you use those parentheses just like I did right there. Otherwise, the answer will come out wrong. All right, and you should get 16 years. Okay, so it should take about 16 years for the $10,000 to grow to 45,950 if you have 10% compounded annually. In other words, they'll calculate the interest. They'll give you interest on your money once a year. All right, solving exponential equations using logarithmic properties. To solve an exponential equation using logarithmic properties, rewrite the equation with a base raised to a power on one side. Take the logarithm base e or 10, in other words, natural log or log, of both sides of the equation. Use a logarithmic property to remove the variable from the exponent and solve for the variable. Okay, so this is what we're going to do. Okay, so we are going to take, so when you have an x in your, when your variable is an x and it's in the exponent, we're going to do logarithms. All right, so we're going to do log of 4,096, oops, there we go, equals log of 8 to the 2x. Okay. Now what we can do is we can take this exponent, remember this is logarithm rules that you need to know, and we can move it up to the front here as a variable, as a multiplication. All right, so we'll have log of 4,096 equals 2 times x times log of 8. All right, now what we're allowed to do is we need to get x by itself, so we're going to just divide everything off that we don't need. 2 times log of 8, divide on both sides. All right, so we say x equals log 4,096 over 2 times log of 8. Okay, now again, make sure you use parentheses appropriately. And now be careful on this problem when you plug this into your calculator. I'm going to write out how you should type it into your calculator. So you should type it in this way. Hit the log button, parentheses 4,096, divided by, parentheses, 2 times log parentheses 8. Okay, if you type it in like that, you'll get it right. If you neglect these outer parentheses, you will get the wrong answer. So be careful. And in this case, you should see the answer should be 2. Okay? Okay. All right, here's another problem. Now we're going to do this one a little bit differently. So what we're going to do, of course, as we normally do, we're going to get that exponential part by itself. So let's divide by 6. So we get 4 to the 3x minus 2 power. Oh, I'm sorry. That's one thing I was going to say. This is a typo. Change that to a 96. So that's a typo. Okay, not 120. It should have been equal to 96. All right, so 96 divided by 6 gives us 16. All right, now what we're going to do is we're going to use a process called, well, it doesn't have, I don't know what the official name, but we're going to get these bases to be the same. Once the bases are the same, we can set the exponents to the same. So we notice we have a base of 4 here, and we have a 16 here. Well, what we know is, oops, let's rewrite this. But we know 16 is actually 4 squared, right? Okay, 4 times 4 is 16. Now, once we have these bases the same, we're allowed to set the exponents the same. Okay, so in other words, now 3x minus 2 equals 2. Nice and easy, right? So once you get these bases the same, you set the exponents equal. And then it's just algebra. So we'll add 2 to both sides. We get 3x equals 4. Divide by 3. And we get x equals 4 thirds. Okay? Again, there's other ways to do this. You can use the method we just used in part A. You'll get the same answer. Okay? All right. Oops. All right, so we're going to solve this one by converting to exponential form. So there's a 4 here, right? So we can get rid of that by dividing both sides by 4. So we'll get log base 3 of x equals negative 2. Okay. All right, now we convert to exponential. We do that loop around just like that. So we get 3 to the negative 2 power equals x. So we know that x equals, remember, negative 2 power. A negative exponent means flip the fraction, right? So this will be 1 over 3 squared, which is 1 over 9. Okay? And again, you can always plug this in to the original, and it should calculate out. Okay? All right. All right, now this next one, we're actually going to skip. All right, so we're going to go on to example sales decay. All right, after the end of an advertising campaign, the daily sales of Genapet fell rapidly with daily sales given by this function here. So notice right away we have an E right there. Okay, in dollars, so S is in dollars, and X is the number of days from the end of the campaign. So for how many days after the campaign ended were sales at least 1,980? So we got to think of that phrase, at least. At least. If I'm going to give you at least $5, that means $5 or more. Okay? So that's greater than or equal to. So we're going to say we want this equation to be greater than or equal to 1980. All right, so we write it out, 3200 e to the negative 0.08x greater than or equal to 1980. Oops, 1980. Here we go. All right. Now we're going to divide both sides by 3200. Okay. So we'll get e to the negative 0.08x greater than, and if you do 1980 divided by 3200, you get 0.61875. Now what we're going to do is, since we have an e here, remember we're going to use the natural log. Whenever you have an e, use natural log. They go together, and I'm going to show you why in a second here. So we're going to natural log both sides. That allows us by logarithm rules to bring this to the front as multiplication. So we have negative 0.08x times natural log of e, greater than or equal to the natural log of 0.61875. Now, natural log of e, this is something I told you to learn, memorize in one of the previous sections in this chapter. Natural log of e equals 1. So we're doing negative 0.08x times 1. In other words, we no longer need the natural log of e. It's equal to 1 and we're multiplying by 1. So we're going to divide by negative 0.08. Okay, so we get x left over. Now, we're dividing by a negative. So remember, when you have inequalities and you divide or multiply by negative number, flip the inequality. So now we're going to say x is less than natural log of 0.61875 over negative 0.08. Now, if you plug that into a calculator, you're going to get something around 6 days. Okay? Plug that in, make sure you can do that. All right, section 5.4, exponential and logarithmic models. All right, so this is a problem we're not going to do in these notes. I would do this if we were in person because everyone needs to have the right calculator for these. You can Google how to do these. It's going to be an exponential function. Okay, so will not be on the test. If there's any problems in the homework on this type of problem where it asks you to plug into the calculator to find the model, please let me know. I think I took them out, but not 100% sure, and I will fix those. All right, this we're going to talk about, though. So constant percent changes. So if the percent change of the outputs of a set of data is constant for equally spaced inputs, and then an exponential function will be a perfect fit for the data. If the percent change of the outputs is approximately constant for equally spaced inputs, an exponential function will be an approximate fit for the data. In other words, it'll be good enough to make predictions. All right, so here's the set of data, right? So we have the months here, 1 through 8, and then the sales in thousands. So what we're going to do is we're going to look at these numbers here. We're going to look first at the difference. Okay, they've called it the first differences. So in other words, how did we get from 780 to 608? Notice we subtract 172. Okay. Next step, how do we go from 608 to 475? We subtract 133, and we keep doing this, right? We keep seeing what's the difference. What are we subtracting each time, or adding, depending on the problem, of course. So these are all the differences between each of these sales outputs per month. Now what we do is we calculate the percent of change. How much did it change from 780 to 608? And we notice it went down by 22.1%. For the second month, sales went down 21.9%. Third month, fourth month, etc. Notice what's happening. 22.1, 21.9, 22.1, 21.9. Well, these two numbers are very, very, very close together, right? Okay. So the percentage change is approximately 22%. So that's what they set up here, right? If the percent change of the outputs is approximately constant for equally spaced inputs, then an exponential function is an appropriate fit. Okay, so this means that the sales 1 month from now will be approximately 22% less than the sales now. All right, and so these are exponential models. If a set of data has an initial value A and a constant percent change R, written as a decimal. So R is your rate in decimal form, so make sure you know that. A is your initial value. For equally spaced inputs, X, the data can be modeled by the exponential function, this guy right here. Okay, so this is a function to know. So this is for growth. We're going to add the percentage each time for growth. Of course, if we're losing money or decay of some sort, then we're subtracting that rate. Okay, all right. All right, so here's an example. So suppose inflation averages 6% per year for each year from 2000 to 2010. This means that an item that costs $1 one year will cost $1.06 1 year later, and the second year the 106 will cost increase by a factor of 1.06. In other words, 1.06 times 1.06, in other words, 1.06 squared, right? That's if you're increasing by the same percent each unit of time, in this case years. All right, so write an expression that gives the cost t years after 2000 of an item costing $1 in 2000. Okay, so the cost of an item is $1 in 2000. Increase at a constant percentage rate of 6%, so we plug in plug in 0.06, that's 6% as a decimal, and we use the formula that we were given up above, this one right here. Okay, and that's what they did. So the initial amount's 1, the rate is 0.06 in t years. And we can simplify. Well, multiplying anything by 1 stays itself, right? So they're saying we can simplify this formula to 1.06 to the t power. Okay, so you just plug in however many years for t and calculate. All right, so part B, write an exponential function that models the cost of an item t years from 2000. If its cost was $100 in 2000, we're using that same equation, right? A is 100, the initial, 6% increase per t units of time. Okay, we can simplify it to right there, 100 parentheses 1.06 to the t power. Make sure when you do these problems, again, order of operations, your PEMDAS, right? Exponents first, then multiply. And part C is going to help us practice that. So use the model to find the cost of the item from part B. So we're going to use this one right here. Let me clean that up for you. So we're going to use that model right there. Find the cost of an item from part B in 2010. So remember, T is years from 2000. So 2010 means T equals 10. All right, so let's see. All right, so the cost is 100 times 1.06 to the t power, but we're using 10 for t. Now we plug this into your calculator. Plug it in just like I did. Use parentheses appropriately. If you do it piece by piece, make sure you make this calculation first, then multiply by 100. PEMDAS, always. Order of operations, always. If you do that, you should come up with something like $179.08. All right, there we go. All right, so these two sections were a little bit short, but still make sure you go over these, make sure you do your homework. Thank you.